Hey everybody, Milk's here, and MoNaCo too. Getting right into video number 3, page 6 and 7.
We're talking about the acid-base theories. We said something about them in our vocabulary. We are going to get into the differences about them now.
Sure.
Gotta know these details.
Yeah, sorry this one might be a little longer, but this is the nuts
down.
and bolts of the unit, guys. This one's going to be important to make sure we know all this stuff cold.
So, Mr. Milks, what exactly is an acid? Because I've seen like aliens at the blood with the acid, and it's just like eats everything away, and it's like,
Sure. Sure.
Is that real or is that Hollywood?
Well, acids are basically what we call caustic, which means they will burn, right? They're caustic, so that part is real. What it is specifically, as far as we're concerned, is any solution that has a higher concentration of H plus ion or that hydronium ion. Has a higher concentration of that than OHs. Why don't you show me real quick what this whole H plus ion is, Mr. MoNaCo?
I.
All right, so let's start with this. We got a hydrogen atom. 1 proton, 1 electron.
It's a Lewis dot structure of it.
Lewis dot, there you go. In order to make the ion, I must lose that electron. And now I got a charge. Beautiful. Now, just so we're clear, Mr. MoNaCo and I will refer to this thing as an H plus ion, but we will also refer to it as a
hydronium ion.
Or a proton.
Or a proton, yes.
Because that's all that's left here is a proton. It was a hydrogen, had 1 proton, 1 electron. Bye-bye electron, all that's left is a proton.
Yeah. So that is a proton, which will do something interesting when it bumps into a water molecule.
So why don't you show us? Cool. Let me get a water molecule up there. Right, H2O with my 2 sets of lone pair electrons. Now, hydrogen itself has 1 and wants 2. This hydrogen ion now has none. So where's that hydrogen ion going to go?
Well, it's positively charged. So it's going to get attracted to negatively charged things.
Right.
And I can see from my water molecule there that there's a negative side of it with got these extra lone pairs of electrons on it.
And
so
hydrogen does want how many electrons anyways to be full?
It wants 2.
It wants 2.
Right. So it'll form a coordinate covalent bond like a so.
So the H is going to come on over to one of those lone pairs, and the definition of a coordinate covalent bond, and we didn't do this in bonding, is a covalent bond where one atom supplies both of the electrons.
Yeah.
This H plus didn't bring any electrons to the table, but he's going to hook on there to get the 2 that he wants, and now I've added a proton onto this thing, so I have a plus charge.
Right.
This is a schematic of what that H3O is.
Right.
So whenever I have an H plus in solution, I will always have H3O in solution. So that's why when we say they're synonymous, they mean the same thing. If I have one, I have the other.
It's a question of what does the H plus, the proton, do when it touches water? It forms H3O plus. That's why they are the same. And acids and bases need to be in water aqueous solution. So there's always H2O molecules around.
Yeah, always.
Always.
So there's going to become an equilibrium now. As one H plus hooks onto one H2O, an H is going to come off of one of the H3Os, and there's just going to be this equilibrium going on.
Yeah, we'll get to that next unit, but let me go erase that.
Sweet. So then we get into what exactly a base is. So a base, specifically, is a solution that has a higher concentration of hydroxide ion than it does hydronium ion. They're generally bitter and they're generally slippery.
And the hydroxide ion is an ion that just kind of falls off of an Arrhenius base.
Correct. It's got an OH in there somewhere and it comes popping off.
If it steals an H plus away from an H2O, it creates an OH negative in the process. So it's forming and breaking at the same time.
There you go. Okay, so let's get into Arrhenius theory. The Arrhenius theory states, Mr. MoNaCo,
that acids produce H plus / H3O ions and bases produce OH negative ions in solution.
Sure, and this was a pretty good theory for quite a while.
Yes, and let's see what that formation involved.
So an acid dissociates forming an H plus or hydronium ion as the only positive ion in solution.
Right. Do I need to draw an equation for any of this? That's pretty straightforward.
I think it's pretty straightforward.
Yeah.
Do you have the urge to draw on the board again?
I do, but I'll do it real quick while you
All right,
click
how
on the
about
next one.
HCl?
Yeah, I think I'll do that. I'll do hydrogen.
Chloride, so HCl, hydrogen chloride, plus water is going to form hydronium ion plus chloride ion. So that H basically, can you circle the H in the HCl? And then draw an arrow over to the H2O. Because the H is going to come off the HCl and go onto the H2O. That's where I get this H3O. And that's all that's left from the HCl is that Cl minus. Now the Cl minus in solution means nothing to us. We're dealing with H pluses in this whole unit.
Right. The chloride ion's a spectator.
Yeah.
It's just doing its thing, floating around.
Sure.
And so that was the formation of the hydronium from the simple strong acid hydrogen chloride or hydrochloric acid.
Very good.
Cool. I'll erase that while we go to the next.
Sweet. Arrhenius base is going to form OH. So specifically, a base dissociates, forming OH minus ions in solution as the only negative ion.
And if I draw a quick scribble out of this, we'll do
Okay.
sodium
That's
hydroxide.
most common, yeah. NaOH. He's going to react with, he's going to be in the water.
That OH steals a. Oh wait, it's not two OH. One OH.
There you go. And H2. There you go. There we go.
My bad.
That's okay. So basically the Na and the OH dissociate, and all of a sudden there's OHs floating around in the H2O. Okay? This one's a little bit, this one isn't as coherent as the H+, because the H+ forms that H3O.
Right. If you
This
really
one doesn't.
wanted to look at it, the OH negative does other things, but we will talk about that one-on-one if you want to know.
Yeah, or we'll get into alternate base theory before too long. So, moving on. Ooh, MoNaCo's favorite.
Polyprotic Arrhenius acids.
Yeah, basically I can form more than one H pluses sometimes.
Right.
So what's a monoprotic, MoNaCo?
Mono means one. Protic means proton. So Arrhenius acid is Arrhenius acid that has to release one proton.
For every 1 mole of acid in it.
Right. So like hydrogen chloride, hydrochloric acid is a monoprotic Arrhenius acid.
Okay.
Because it's only got one hydrogen atom to donate.
Right. We can see
Or
this.
lose.
We can see in this example on the left side I got HCl together.
Add
On
H2O to it.
Right, and on the right side I got H plus and Cl minus. That's where it dissociated.
Mm-hmm.
Okay. I could write this a different way though.
Yes.
I could write it with the hydronium ion in there.
Mm-hmm.
Right?
Yep.
And if we look, if I take that H plus and that H2O, they combine to make that
H3O.
H3O. So that's why they are synonymous. Are we good with
Cool.
this?
Yeah, I'm good with that.
You good with that? All right. So now diprotic.
Di means two, protic means proton, so two proton Arrhenius acids. Oh, so it produces two H pluses or H3 pluses for every mole of acid that is created.
Okay. So there we go.
So
Sulfuric
sulfuric
acid.
acid, H2SO4, combines with water. It releases two H pluses and an SO4 sulfate and two waters.
Right.
Another way you could show this, though.
With the hydronium ion in there is
Right.
my H2 in the H2SO4 becomes two H3Os.
Right. Can I circle them real quick?
Okay.
Cool.
So the two H plus ions hook up with the two waters to form the two H3Os.
These two equations are showing us the same thing, by
The
the way.
exact same thing, because remember, H plus and H3O plus are synonymous.
And if you check for conservation of mass, both sides, both equations are in fact balanced as well.
Very good.
Cool.
Very good. So, triprotic, same thing, except for now 3 moles of H plus in solution.
Right.
So we need something like this guy here.
Phosphoric acid.
Ooh. Phosphoric acid, see the 3 H's in it? I
Yep.
can form 3 H plus ions with my 1 phosphate ion.
Cool.
Another way I can write it.
Nice. Let me circle some
Okay. So
protons and
I'm either going to form 3 H plus ions or 3 hydronium ions. means the same thing. And Mr. MoNaCo just drew how that hydronium ion is actually formed. So we understand that it is the same thing going forward.
For sure.
Okay? But guess what? There's some problems with this theory.
Always exceptions.
So the exception here is that not all bases have OH physically in the chemical compound itself. There isn't specifically an OH in there.
Right.
So they have to create an OH ion in solution in like an indirect method, if you will.
Right. And the reason why we know this is because you can go around with pH paper, pH probes, and test to see if things are acid or basic. And you know the formulas, and some things out there will behave like bases, even though they don't have that hydrogen ion or atom out in the front of their formula.
Right. Well, that would be the acid.
Right.
Right. And then the OH in it towards the end
would make it
a base.
So some things behave like acids and bases without Arrhenius' explanation working.
Right. So let's just go over Arrhenius one last time. We'll
Basic
review it,
rules.
and then we'll get into the difference. So there you go, MoNaCo. Go.
Arrhenius acids dissociate. They produce protons or hydronium ions in solution.
Okay. Physically produce them.
And Arrhenius bases dissociate, producing physically hydroxide or OH negative ions in solution.
Right. And what this basically means is that H plus is in the acid, or the OH minus is in the base, physically in there.
Right. Part of the molecule.
Correct.
And that's what makes them easy to identify on paper, because you see, oh, there's an H in here, and it's at the front. There's an OH in there, it's at the end. Wow, it must be an acid. That must be a base.
Well, let's get into the classic
alternate theory.
Yeah, and there's one classic molecule that really is why we need to do this.
Ammonia.
So, there it is. So acids are now H plus donors, and bases are H plus acceptors. No OH now in the talk. Okay?
Right.
We'll show you how this works. So acids basically
give off H plus, producing H plus ions in solution, or those H3O, as I showed the formation of that.
Yep, very similar.
So that Brownstedt-Lowry acid donates a proton to the water molecule, making H3O plus. It fits.
Yeah, the donor and the give off is the same.
Right.
Okay.
Bases, on the other hand, accept the H plus, producing OH negative ions in solution. So
there's that water thing.
Right. So water acts as the base sometimes because it accepts the proton from somebody else.
Sure.
And as a result, it makes an OH negative ion in solution.
Right. Well, or to go back to Arrhenius theory, it provides that OH because the base actually accepts the H off of it.
Right.
So that OH in solution is coming from the actual water itself.
Right. OH is formed in situ by the loss of a proton because it's donating it to another base.
Right. So
the base
here's the
accepts
classic
the proton from
here's
water.
the classic example.
Ammonia, NH3.
Has no OH in it.
Nope.
So it doesn't just dissociate to form OH ions in solution.
Can't be done. But if you tested the pH of an ammonia solution, you'd find out that it's quite basic.
And it's slippery.
It's nasty. It's a great cleaning product. And this is what's up.
So basically a hydrogen from the water
Gets stolen.
Gets stolen by the ammonia.
Which is accepting the proton.
Correct.
Becoming, what do you call that?
Ammonium ion, which is in table E.
And F. Yes, for sure.
Right.
Yep.
When in doubt, check E out.
Yep.
And this has the same classic, what's that bonding called again?
Coordinate
covalent bonding. That lone pair on the end is going to be the two electrons that the H hooks onto.
And so the water H2O molecule is not an H2O anymore. It lost a proton to the ammonia, so it's OH negative.
Now
so the OH negative was created during the whole donor-acceptor process that ammonia plays.
Correct.
Kind of cool.
Kind of cool, and it's very robust now.
Yeah. This explains all acid-base behaviors.
It does.
Except for when you get to organic chemistry in college, but look up Lewis acids if you're confused.
Yeah, no,
don't
we're
do
not
it,
going
don't
there.
do it.
No. We're not dealing with electrons. We're dealing with protons.
So,
guess what? Hey, long video,
that's it.
but it's man, and it was some real meats and potatoes. It is.
Right. So I wouldn't be
For this
surprised if
section.
you don't necessarily understand every little step at this point. So come and have a conversation with us. If you've
Let's do
paid
it.
attention, we'd love to have a discussion.
Absolutely.
All right. Thanks for
I'm
watching.
serious.